Okay, let me talk a little bit about the inverse trigonometric functions. This is section 10.6. Now, I like to talk about this because it's important to understand about inverse functions in general, how you obtain them, how their domains and ranges are related to the original functions, and so on. Right. Now, in fact, the inverse sine and inverse cosine function are quite straightforward. Here's a graph of the sine. You should remember that the graph of the inverse function is the original function flipped about the 45-degree line. So I draw a 45-degree line. Of course, we know this is pi over 4, but if you flip this around, that means that the points down here will go up here, and the points up here will go down here. So if you can imagine putting this on a stick, right? This is a stick, this light blue thing, and then you put a wire that looks like this. And then you just twirl around the wire, and you see what it looks like. Now this point here on the x-axis, that's pi, is going to twirl up to the same point on the y-axis, which is pi. So you can see that this point here is going to go up to this point here. Right? So similarly, this point here that's at minus pi on the x-axis is going to go down to the point at minus pi on the y-axis. So twirling around the 45-degree line exchanges the x and the y, which is exactly what you want to do for the inverse function. Okay? So naturally, if you have this sinusoid, this wave that's a horizontal wave, if you flip it, you get a vertical wave. That causes a problem because you know that a function has to satisfy the vertical line test. Each vertical line can only intersect the function once. Otherwise, you'd have two different values for the function. For instance, if I take a vertical line here, that intersects 2 points. So my question is, what's the value of the function? I'm going to have to choose one of them. So an easy choice in this case for the sine, an easy choice is to choose the value between the y values between minus pi over 2 and pi over 2, and I've made this in red. Okay. Now we know that the sine of a angle must always be between minus 1 and 1. Okay. So if you look at the inverse function, that means the domain of the inverse function, that is the domain of the domain of the arcsine, must be between minus 1 and 1. So the domain of the inverse function is equal to the codomain of the original function. Okay. Now the codomain of the inverse function is you usually have a choice. Here we have a choice to go between minus pi over 2 and pi over 2. I could also choose between pi over 2 and 3 pi over 2. I could take this segment up here, starting from here and going up another pi. I could keep going like that. Now you notice that you're always going to have some interval of pi. I could go from minus pi over 2 to minus 3 pi over 2. So you can see that it's actually going to always be something like it's always going to be n times pi over 2, or I should say like this, 2n plus 1 times pi over 2. And then it will be, or I can make this even better here. I think it's easier to do this way. The basic one is pi over 2 and 3 pi over 2. But I could add n pi to that. Okay. So these are the possible domains for the arcsine. Now, we typically choose this one. This one is the preferred one because it's convenient, right? Go from pi over 2 to 3 pi. No, I'm sorry. This is not the convenient one. The convenient one is this one here. Sorry, this is the convenient one here. This one is not convenient. Let me erase that so it's not confusing. Okay. This one is not the convenient one. From minus pi over 2 to pi over 2, that's convenient. Okay. Now, we also have a similar situation with the arc cosine. We do the same thing. We also flip the cosine around the 45-degree line. And you can see that you get the result. This point up here flips down to this point up here, flips down to the point down here, right? And this point over here flips up to the point up here. This root here, which is at pi over 2, flips up to pi over 2 here. All right. Now here we've got one. Here we just have one arc of the cosine, one section of the cosine. If I flip just this section up, then I can get a function. If I go any farther, I'm going to double back, and I won't satisfy the vertical line test. So it's natural to have a domain well, domain minus 1 to 1, it's natural to have the codomain be from 0 to pi. Now, you can also do the same thing with arc cosine that you did with arc sine. You can choose different codomains. You could add any multiple of pi to this codomain. Okay. Now, for tangent and cotangent, I'll refer you to the book. There's this very similar argument here. The nice thing about tangent and cotangent is that the domain is not limited. So, for instance, if you take tangent looks like this thing here. If I flip it around, then my x values can be anything, right? Because the range of tangent is all of the real numbers, right? So here now the codomain of the tangent is, the domain of the tangent, of the domain of the arctangent are all real numbers. Here I chose the codomain to be minus pi over 2 to pi over 2. Again, I could add any multiple of pi to that domain and get another, I could add any multiple of pi to that codomain and get a different codomain. Okay, so you have a choice of codomains for arctangent. You also have a choice of codomains for cotangent. All right. Now, when you get cosecant, and secant, it's a little more complicated. Let me go there. But the idea is the same. In fact, you can choose the same domain. Well, it's easy to choose the codomain, the domain of secant is going to be basically the complement of the domain of cosine, right? Because secant goes between minus 1 down to minus infinity and plus 1 to plus infinity. And so does cosecant. Let's just take a look at that quickly. We can see those domains here. But we can choose the codomain of secant to be the same as the codomain of cosine. All right, so here's your secant. So you have a bunch of different choices. Here you can see that the domain goes from minus 1 to minus infinity, plus 1 to plus infinity. Again, we can choose different multiples of pi. We can take this basic domain from 0 to pi, codomain from 0 to pi. Of course, pi over 2 is not included. Or you can do some shift of that. Okay. All right. So that's kind of introduction to arc functions. There are several functions here. One thing to notice, this seems like there's a lot of problems in this section. A lot of them are just completely trivial. Notice that when you take the arc cosine of the cosine of an angle, then you always get the angle back again. If you take the cosine of the arc cosine, you don't always get the angle back again. So there's some trick questions here. You can see that if you look at the answers. For instance, here, let's get there. All right, these are really all straightforward. Just think about, if you think of this here, arctangent, you think, what angle has tangent 0? Okay. All right, what angle has cotangent square root of 3 over 3? Okay. And then you also need to think about the codomain. The codomain of cotangent is between, well, I don't remember what it's between. I guess it's between 0 and pi or something like that. You can check in the chapter. I know the codomain of tangent is minus pi over 2 to pi over 2. I do know that. So you have to choose the angle that's in the correct codomain. Okay, so those are very straightforward. Now, one thing, again, you need to be, so let's look at this here. Okay, so if you look at these, if you take sine of the arcsine, you might think, well, since sine and arcsine are inverse functions of each other, the sine of the arcsine should just give me 1/2 back again. And that's often true, but that's not true for all of these. For instance, for 61, you have to be careful. Okay, so you can think about why something is wrong there. And also 66, there's something wrong there. So you can think about why that is. Okay, so I was going to do a couple of exercises here from the later part. So I want to express this here, cosine of arcsine x plus arctangent x, as a function of x. So we want a strategy for doing these things. Okay, so I want a function of x. This is actually going to be an algebraic expression in x, even though we have trigonometric functions. So our answer will not have cosine or sine in it. So if I had cosine of arcsine x, I could draw a triangle and figure out what the cosine is. Because if I draw a triangle with sine, where the angle has sine equal to x, then I could find the cosine of that same angle. Okay, so I could do that. If I just had a single arcsine here, I could solve this using a triangle. If I had just had a single arctangent, I could solve this using a triangle. Since I have both, it's difficult. So what I can do is I want to break this expression up into trig functions of arc functions and then use a triangle. Okay, or actually use more than one triangle. Okay, so what you really have here is a sum of angles. Arcsine of x is an angle. Arctangent of x is an angle. So I can use the this sum formula. We know the sum formula here. We know that the cosine of a plus b, right, I'm going to use this formula, cosine of a plus b equals cos a, cos b, minus sine a, sine b. Okay, and that's the formula I'm using here. This is my a, this is my b, right? This is my a, this is my b. So here's my a, here's my b, right? A, b. Straightforward application of this formula. Okay, now all I have are cosines of, I have functions, trig functions of arc functions. So I can go ahead and draw the triangles. Now, arcsine of x, what does that mean? That's the angle whose sine is x. Okay, so all I need to do is draw a triangle where the angle has a sine x. Now the sine is going to be the opposite over the hypotenuse, right? So this triangle here, x over 1, has sine x. Then I can solve for this other side using the Pythagorean theorem. Remember, be careful because this is not the hypotenuse, so it doesn't have a plus, it has a minus. Okay, if you can check that this side squared plus this side squared is equal to 1. All right, so we've got this. Now if I want the cosine of this angle, I just take adjacent over hypotenuse and I get this value here. Okay, now one thing you should check is whether this works for x positive and negative. Now if x is negative, the triangle flips down, but I still have the same cosine. Okay, so this is true whether or not x is positive or negative. So we're good there. Okay, so you always take the positive square root. Now let's take the one where we want arctangent. If we have arctangent of x and we want to find the cosine and sine for that. Okay, now if the tangent of the angle is x, so I should have put a phi here. This is a phi here. If the tangent is x, then that means the opposite over the adjacent is x. So I can label it this way, x and 1. Then I need the hypotenuse. Use the Pythagorean theorem, square root of 1 plus x squared. Then off of this I can read the cosine and the sine of this angle theta. And once again, this is true whether or not x is positive or negative. If x is negative, it will flip down. I still get the same relation. I still take the positive square root. Okay, so now all I have to do is plug in these values. I have, here I want theta is arcsine of x. So I want cosine of theta, right? So let me just shade my stuff here. I want cosine, I want this here. Cosine of theta is just this, right? Okay. Because theta is my arcsine. Then what about the other one? Well, cosine of arctangent is just this one, because my theta is my arctangent. Okay. Now what's sine of arcsine? Well, if x is in the right domain, then this is just going to be x. Okay. And what's sine of arctangent? Well, that's this one here. That's this one here. Sine of arctangent is just this one here. All right, so I just plug in these algebraic expressions and I will get an algebraic expression for my answer. Okay, now the question is, under what domain is this valid? Well, if you look at this, you certainly can't have x be bigger than 1 because then you'll get a square root of a negative number. Okay, now in fact that's going to be true because you can always define, so here, let me write down here. Arctangent is defined for any x, but arcsine is only defined for x between minus 1 and 1. So this relation will hold for minus x between minus 1 and 1. All right, so that's how you would do that problem. Right. All right, now another set of problems down here. So this is I asked you to look at is let me go here. I should be able to get this and this, make this a little bit bigger. Okay. All right, so I want to find the domain of a given function. Now this looks kind of complicated, but it's really not so complicated. Here I have arcsecant of x cubed over 8. All right, now what is the, so what I need is I need the domain of arcsecant. Okay, this can only be, so if I get the domain of arc secant, then I can get the domain of this function. Now, notice that the codomain of secant is secant must have absolute value bigger than or equal to 1. So that means that the domain of secant must be the same. That when you define secant, if you define secant of z, z must have absolute value greater than 1. Okay, so if I want to have this be defined, then this thing here, this value here, must be greater than or equal to 1. It must be in the domain. So that's where I get this condition. Okay, so that's all I need to do. And then I solve this for x. I get x greater, absolute value of x greater than or equal to 2. They ask for interval notation, so this is my final answer. Okay. All right, so here are a few sample problems for you to look at. And we'll talk about these more next week.